Okay, I thought I would just make a short movie just to consolidate on what was looked at in today's lecture, where we were considering how to predict the takeoff performance of a conventional fixed-wing aircraft. Having chatted to some of you since the lecture, it seems to me that some things weren't entirely clear. So I'm just going to go through some of these ideas again, just to consolidate what we did today. So the first thing we decided was that we were going to split up the takeoff roll of an aircraft into four components. Um, Obviously, the largest part of this is the ground roll along the runway, and then the aircraft gets to a point at which the pilot or control system decides it's going to rotate, and so there's this rotation phase as the nose of the aircraft lifts up. There's a transition phase as the aircraft goes around an arc into a constant climb. So let's split up these three phases, and we'll call this first phase the ground roll, and the horizontal distance covered in the ground roll is SG. Then there's the rotation phase, where the nose of the aircraft is lifting up off the runway, and we stated that the convention for this is that that lasts approximately 3 seconds, and you can use that to gauge the distance covered along the runway during that rotation phase. So let's call that SR. Then there's a transition phase. The aircraft transitions from rolling across the runway into a constant climb rate climb, called the transition distance. And we said that usually the takeoff distance for an aircraft is to a point where it's cleared an obstacle of some specified height. Now in the project you're working on, that height is 50 feet. And this takeoff distance is in total needs to be under 500 meters. So this final distance here we'll call S climb, and obviously the total takeoff distance S T0 is the sum of these components SG, and the best way to do this is just to consider each of these four phases of the takeoff roll separately. Now we've already defined the takeoff distance, the takeoff velocity, sorry, of your given aircraft in a previous lecture as being 1.2 times the stall speed. That's a pretty good estimate of the velocity at which your aircraft will take off. And of course, already at this stage in the design process, you've got an estimate for the stall speed of your aircraft. So we can write this down. And it is the wing loading So by this stage what you need to have decided for your design is the wing loading. That should have been done a long time ago. The air density, and you know obviously that's driven by the altitude of the airport at which, or the strip, in your case the dirt strip that you're going to be taking off from, and your estimate, your current estimate for your aircraft's maximum lift coefficient. Now let's specifically consider the ground roll phase. Now we know that we can write acceleration as being the rate of change of velocity, but we can pretty quickly also show that this is exactly the same as v times the rate of change of velocity with distance, or v dv ds. I'm not going to go over that again. So from that we can do a little bit of rearranging to show that ds is is equal to v upon a dv. And of course we can integrate both sides to give us on the left hand side your ground roll. If this integral of course is running from s equals 0 to the point at which you take off, which is from v equals 0 to your takeoff velocity. But the challenge we have for the right hand side integral is that of course, because you might have a constant thrust that's being delivered by your aircraft, because the drag force that's being delivered by the aircraft is a function of your aircraft speed as it rolls and increases in speed down the runway, then this integral on the right hand side, this integral here, is not trivial. But fortunately, as I mentioned in the lecture, we've got a MATLAB code that will numerically compute this integral for us. That's essentially what is going on inside that calculate mission profiles routine within the MATLAB program that I've given you is doing. But of course, to get to compute this integral, we need to know what the acceleration of the aircraft is as a function of aircraft speed, v. So, and we can compute that quite easily, starting with Newton's second law. So we just say that F is equal to ma. And obviously this is the net force is equal to the mass of the aircraft times acceleration, and the net force for the aircraft rolling along the runway is thrust, which you should have a value for. Your engine specialist should be delivering you your thrust value, which may or may not be a function of speed, depending on what engine type you're going for, minus the drag of the aircraft, which will be dependent on the drag coefficient that your aerodynamicist has been working on for the last couple of weeks. And then while we're on the ground, we've got this additional drag term, which is our frictional rolling resistance. So that's our force. You've also been computing an estimated aircraft weight, which you should have at this stage in the project. So obviously to convert that into mass, we need to divide by g. So you've got your takeoff weight estimate, which will divide by g to convert it into a mass, multiplied by a. Now, just to reiterate, this value here, thrust, may or may not be a function of forward speed. Drag certainly will be, even if you've got a constant drag coefficient. The absolute value of drag, which is what this d represents here, will be at least a function of v squared. And you've got a rolling resistance, which as we'll look at in a moment, will normally also be a function of the aircraft's forward speed as it rolls down the runway. But still now we're in a position to write acceleration is given by this formula here. And this is important because we can plug this into this equation here, which is essentially what you need to do using the Bloodhound Performance program, which you've been given, or an alternative method. I know some groups are planning to do this using an Excel program, which is absolutely fine. So the final thing that we need to think about is how does our rolling resistance or rolling friction vary with speed? Well, again, from school, you should remember that friction, a frictional force, can be defined as varying linearly with the reaction force provided by the surface that a body is rolling across. And we define this thing called mu, the coefficient of friction. But the reaction force of our aircraft will not simply be the aircraft weight, because as the aircraft accelerates, it will be starting to generate lift. So the reaction force provided by the ground will be the takeoff weight minus any lift that the wings are producing during the ground roll. So actually the reaction force provided by the ground will be decreasing, so the rolling resistance will be decreasing as the aircraft accelerates down the runway. And again, you can, so this is F, and we can take this relationship here and put it into this equation here. And again, this should really be accounted for in your performance modelling. I've also given you in the lecture notes some typical values for different types of surfaces for this parameter here, the coefficient of friction. I think I suggested for the aircraft that you're designing to take off from a dirt strip in the Australian outback that a value of mu of 0.04 would be a sensible number to pop in here. So once you've got all of those values, you're in a position to work out the thing that you're interested in, which is going to be the primary component of your takeoff distance, your SG here. It's an integral that you have to compute, and the best way to do this, given the data that you've got as inputs to this integral, is to integrate this numerically, and we've given you a code to allow you to do that. So moving on to the second component of the takeoff distance. Because, as I mentioned earlier, the convention is that it takes 3 seconds to go through this rotation where you raise the attitude or raise the nose of the aircraft to generate enough lift for it to take off. That process takes 3 seconds. It's trivial to work out the distance that the aircraft has travelled, and it's simply a case that the rotation distance will be 3 times takeoff velocity. Obviously you need to have your takeoff distance and velocity in appropriate units just to directly apply that formula, but it's literally as simple as that. So although the ground roll component involved complex integrals, the rotation component, this assumes that for those 3 seconds the aircraft is effectively travelling at the takeoff velocity. In reality, of course, it will be accelerating through those 3 seconds. But just to make life easy for ourselves, we'll simplify it to that. Now, on to the distance travelled through the rotation phase. As the aircraft travels through this, what we'll assume, although it's not drawn very well here, is a circular arc. Okay, so what I'll do is just take that component here, this distance travelled through transition, and draw it again blown up a little bit down at the bottom. So let's assume, and I'll try and draw what is roughly a circular arc a bit better here. Okay, and I've obviously exaggerated the flight path angle that the aircraft's going to end up going at. That's usually we'll let the flight path angle be gamma. So at this point here it carries on at a constant climb rate, constant flight path angle, and up until that point it's been going round what we'll assume is a circular arc of radius, we'll call that radius r, transition. Now the first thing that we can think about, if I can get that back, is what kind of, well, let's draw the aircraft in. So our aircraft has its thrust vector angled in this direction, its drag vector acting in that direction, its lift vector acting perpendicularly to the flight path direction. Oops, sorry, this should have been drag, and weight acting vertically down. Now we know that for rotational motion, or for circular motion, the centripetal force required to get a body of mass m around a curve of radius r at speed v is given by mv squared over r. Now let's assume, unlike I've drawn it here, that the flight path angle that we're transitioning to is relatively small, and that allows us to write that this force is provided primarily by the differential between the lift and the weight. The mass of the aircraft again is going to be, let's assume, obviously we are burning some fuel, but it's effectively still the takeoff weight. So that's our mass. We'll assume again that we're still through this period travelling at the takeoff velocity. Obviously this gets quite a bit more complex if we're taking into account the fact that the aircraft is still accelerating through this phase, so we'll keep our life simple. And the radius is this R transition that I've defined up here. Now if I take the W that's on the left hand side over onto the right hand side, of course this W here is also the takeoff weight. And divide through on both sides by W. And typically we call that lift divided by weight during transition, or lift over weight in general for an aircraft is the load factor for this phase of flight, and of course that now is going to be over G. So there's an equation for the load factor of the aircraft as it goes through this transition phase. So if we equate this expression here with our definition for the load factor during this phase in terms of lift coefficient, then we end up with this expression here for the load factor, or the lift relative to the weight that's required through the transition phase. To get this value, we also need to make that assumption that we made earlier, that the takeoff lift coefficient is 0.8 times CL max. So that assumption, combined with the assumption that the takeoff speed is 1.2 times the stall speed, gets us to this load factor during the transition phase, L upon W. Now from this we can quickly deduce that RTR, this defines the radius of curvature of the path the aircraft is going to travel through during this transition phase, is simply given by V T0 squared over 0.15. You can have a go at proving that yourself. And at a constant climb, so if we assume at a constant climb velocity, if we assume the forces are balanced, so if I go back up to our aircraft going around this, so if we assume that the forward velocity along this flight path is constant, then we know that thrust must equal drag plus W sine gamma. And that relationship allows us to write that v takeoff sine gamma is given by this. And then it's just a simple case of a little bit of trigonometry to get to the point where we can say that the transition distance covered in flying around that arc horizontally is rt, the radius of transition, or the radius of curvature of that transition arc, times sine gamma at climb. So that's the flight path angle that you're aiming to climb at, again, which is something you should know at this stage. And the height that the aircraft will have climbed through during this transition phase, so we'll call this HTR. Now this starts becoming important in making sure that your aircraft can actually work its way above the obstacle, which in the case of the aircraft you're designing is at 500 meters. Okay, so we've now got an expression for the ground roll, we've got an expression for the rotation distance, and we've got the horizontal distance covered during the transition phase, the third phase, and the vertical distance covered during this transition phase. So our aircraft has come round this circular arc, which is the transition. It's gone into a constant rate of climb along a constant flight path angle, which we're going to call gamma. And if we assume it's travelling at the climb speed at this point, we can work out the horizontal distance it will have covered to get to the obstacle clearance height. And again, this is just a little bit of trigonometry. And the horizontal distance in this climb phase, once it's on a constant flight path angle, is simply h obstacle, which is fixed, minus the height that was climbed through the transition, over tan of the flight path angle in this climb phase. So those are the methods of computing the four components. So we've got at the top this integral that needs to be computed to get the ground roll distance. We've got the horizontal distance covered during the rotation of the aircraft, SR, and we've got the horizontal distance covered during the transition phase as the aircraft travels around this assumed circular arc, and finally we've got the horizontal distance covered during the climb. If you add those three components together, you've got the total takeoff distance.